Thank you, Chairman, and also thank you, the organizer, to give me the chance to introduce my study. This topic is about the dead water resistance on the ice floe and in a two-layer fluid. Actually, it's also there is no theoretical in my topic and also no the mathematical. Just is some experiment data, and I hope it can be helpful and it can be as a reference for your theoretical or numerical studies. Okay. Actually, the initial motivation of this research is just I want to study the effect of the straighted ocean and on the drift motion of the platform in deep water. That's because in the deep water and the horizontal mooring, the coefficient is maybe very small. Stiffness is maybe smaller. So the platform can moving with a very large floating motions. So I want to consider if the the motion is stratified, and if the platform moving with very slowly speed, it can be generate the internal wave as an interface. So it can be get the dead water resistance. So this is just the initial motivation and combined to the dead water problem. But here I should thank to the Professor Gou. He gave me a very good comments. His comments is that the effect of the stratified fluid may be affect the stripped motion of the iceberg or ice floe is more meaningful. Like these situations. So because in the polar area and the ocean, the thickness of the fresh water on the free surface is very small. So the larger iceberg or the ice floe, when it has the drift motion, the generation in the internal wave may be very large. So the dead water may be very important. So it's almost the reason why I'm here now. Okay. Okay, now let's see the outline of my topic. This first I will introduce some research about this, and then I will introduce the how to design my experiments, and then give some results and discussions. The results also include several parts. The drag resistance also in uniform fluid and in the two-layer fluid, and also the dead water resistance coefficient. Then I also give some picture to show the picnocline elevations during the experiment. I think it maybe is helpful to analyze the experiment data. Okay. Now let's see some other people's research. Actually, like the most of the numerical method had been done by many researchers, and actually is similar with uniform fluid results method. Here, for example, we can see the Guimac and give the asymptotic expansion method, and also Melon is here now. Use the boundary integral equations and to study the slender bodies, and also we can see the Lintons and et al. They use multiple expansions method, and then green function method, and also Gou. He also gave the talk at the first day of this workshop. He used the nonlinear theory and studied the ship geometry. He studied water problem. So above all, most of the numerical model is focused on the slender body of the ship geometries. Except the numerical method also have some research on the experiment test. Here I will introduce this one. This is a 2D experiment, but it's very clever experiment is that in its experiment, he gave the steady force. That means the force drive the ship is a constant, so the velocity is will be changed. And this one he gave the this is the 3D experiment, but here he focused on the wave weak, back of the structure and at the as an internal wave. So he didn't give the results of the dead water resistance. This one is made by Waters and Brown. This experiment is only, I think it's only one experiment I had to find that focus on the dead water resistance on the ice floe, the box type structures. But this is also a 3D experiment. And this experiment, he focused on the effect of the ice profiles. He gave the four types of ice profiles and compare the results of the dead water resistance. Okay, about all, I think because the numerical method is actually very complicated to study this problem, because box type structure has a sharp corner and a sharp edge. It's not a slender body, it's not a streamline body. And also the experiment, the field experiment results. So here I want to choose the experiment test to investigate the dead water resistance on this kind of box type structure in a two-layer fluid. And also I want to investigate some parameters effect. The important is the draught and the towing speed. So in this experiment, they are varied to achieve the informations and on the corresponding trunks. Okay, this is the background. Now we can see the experiment setup. This is a wheel flow. From this we can see this tool is a tank wall, and this blue one is a box type structure. And this flume is equipped with this a low speed towing system on it. Here is a trail on it. And the size of flume is width is 1.2 meters, and the total length is 12 meters. But in my experiment, I just about used about 7 meters is enough. And the water depth is a constant during this experiment. It's just 0.6 meters, now changed. And this is a side view to see the tank. The black shadow is structure, this one. And this is water-free surface. And here we can see it's clearly it's the internal surface. So the up layer is fresh water, and the depth is H1. And the low red colored layer is saline water, and the depth is H2. Okay, this is layout of the experiment. Next, how to measure. I use the force sensor to measure the drag resistance. Force sensor is at here. Okay, the sample frequency is in the range of 120 Hertz and to the 480 Hertz. It depends on the towing speed. The force sensor here connected the barge and the towing system at here. So when the towing system is moving on, and we can get the force sensor's data on its time series. Actually, the towing resistance should be a constant, we know. But during the experiment, it's not a constant result. It should be oscillations. Why it is oscillations? During our experiment, we also find this. So I must check why it oscillates. We've analyzed the frequency, the oscillation frequency. We find that it depends on the resonance frequency with the total system. So if I filter the oscillations, I can get a constant towing resistance. So that means we can averaging the data over the steady stage, and then we can get the drag resistance like this. This method to deal with the data. Okay, when I get the resistance, we can know in the uniform fluid, the drag resistance can be also written like this form. That means here the C is the resistance coefficient, and S is a wet surface, is the structured wet surface, and here the V is the towing speed. Okay, because we want to maintain the form of this function, so we can do this one. At the two-layer fluid, we can get the two-layer drag resistance coefficient. As a uniform fluid, we can get the uniform resistance coefficient. Then minus this from the two-layer results, we can get the dead water resistance coefficient. Actually, the drag resistance is very complicated. Maybe includes many parts. For example, the friction force and the water wave force, and also the drag form force. But if we minus this one, the left is only the dead water part. That means generate the interface waters. So I use this method. So that means we in my experiment, we should measure this first, and measure it, get that one. Okay. During the experiment, actually first I didn't design to measure the elevations of the picnic line, because I think it's difficult to measure its accuracy. But I think it should be we should record the picnic line, because it can be help us to analyze the trends. So I use a camera and a ruler to record the internal wave elevations like this. Here is the parameters. For the uniform fluid, we text 6 bar draft from 0.1 to 0.24, and 6. And the total speed is from 0.06 meter per second to 0.24. Corresponding to the two-layer fluid, we consider the two situations that is internal phase positions. The first one is the up layer is H1 is 0.2, and the lower layer is 0.4. And the second one is the up layer and the lower layer, also 0.3 meters. These two situations. For the first situations, we consider the 4-bar draft from 0.1 to 0.2. So the non-dimensional draft is the bar draft divided by H1 is from 0.5 to 1. Okay, this is also the turn speed. During the two-layer fluid, the rho 1 is this, rho 2 is this. The ratio is 0.973. I didn't change this one. Okay, now this important part is I show some of the experiment results. First is drag force in uniform fluid. This picture is typical results of the drag force in uniform fluid. This is the drag force versus the towing speed, and the draft is 0.1 meters. Maybe this is can't see very clearly, but if we change the horizontal axis as velocity, the square of velocity, we can find the resistance is directly proportional to the square of the towing speed. Okay, so that was based on these functions, we can find that means the coefficient here is equal to a constant. It's not changing. If the we can analyze the results. Why is a constant? Because the drag force can be separated several parts, the friction and the form drag and wheel makings. But because these cases, the towing speed is very, very slow, so this part and this part can be neglected. It nearly to be zero, trend to zero, and only this part is the dominant part. And this part is proportional to the square of the speed v. So the total force has these trends. Okay, this is drag force in the uniform fluid. Next one is drag force in the two-layer fluid. First, it's a little bit complicated. We must make the two-layer fluid situations. Here is density profile. This is because before the towing test, we make the two-layer fluid like this. The peak neckline thickness, about maybe like here, is about 0.05 meters. But if the structure is moving on the free surface, is a turbulence, so the density profile will be changed. So it's not like the experiment, not like the numerical method. We can give the constant these situations, but in experiment it couldn't. It almost will be changed. So this one is the draft is 0.1 meter, and this one is 0.2 meter. This one is relative deep draft. So the disturbance is very heavy. So after several towing tests, will be checked the profile. So for example, like this one, we must to make the two-layer fluid again, and to continue the experiment. This is okay. This two diagram is drag force in two-layer fluid, and this one is two situations. Here, the blue one is dimensional draft is 0.5, 0.6, 0.7, and 1. From this, we can see during the with increase of the draft, and the resistance is also increasing, and this is the same trend. So for at the same time with the shallow draft, for example, like this one, the increase is approximate linearly with increase of turn speed. But for this kind of will be have a local maximum, but it's not very obvious, not clearly. But here we can compare with just we had did the uniform towing results. We can compare together. Now these two pictures just with a different draft, and this one is shallow one, and this one deep one. The red one, the red circle is the results in two-layer fluid, and this blue one is in uniform results, and minus is green one is dead water resistance. So from here, it can be clearly if the towing speed is very slowly or is very large, then the dead water resistance is trend to zero. But only at this area is this is very important part to the drag force, because like this at here maybe is almost twice of the drag force in of the uniform results. Okay, we also compared the published results by Ekman. He also did the experiment, but for a slender ship, and in his results, this curve number by 5 is experiment data, and this line number by 1 is uniform data. For this curve, we can find that his results has a local obviously local maximum at here. So that means if the ship overcome the dead water force at here, the velocity maybe from here just jumped to here. So, but our now in these box type structures, no, we can. They are not the situations. It couldn't be have the velocity jump opinion. Okay, the phenomenon. Okay. Now here we should check the dead water resistance. This is a 9-dimensional results, and the horizontal axis is the internal Froude number. The internal Froude number is defined by the towing speed and divided by the wave speed in two-layer fluid. It depends on the difference of the density and the layer, the interface positions. And here we can find the results is also the trends is very clearly. This one is a shallow draft and this is a deep draft. These two situations have actually the similar results. And we just give this to analyze this structure. Analyze this picture. We can find the CD attains the maximum results and the corresponding Froude number downshifts slightly with the increase of the draft from here to here. So like this one. And another conclusions we can be seen that when CD gets the maximum and the Froude number is much smaller than the critical Froude number unity. It's just about maybe nearly about 0.5 to 0.6. Okay, sorry, this. Okay, this result is in Mello's published paper, and this is also the resistance coefficient, and the structure is different. It's a prolate sphere and it's a slender body, and when the CD gets a maximum and the Froude number is about 0.9, yes, is higher than the present results. This result is published by Gou. He also introduced as Monday his talk. From this, we can see he divided the 9-dimensional, the square of the 9-dimensional draft, and get this result at here. So at this area, that means when the Froude number is close to the critical Froude number, and the result is irrespective of the draft, only depends on the Froude number. Actually, I also did this. I also deal with the experiment data, and we also find this trend is similar with the numerical results. And also we can find this one is shift down and shift down slightly with draft is deeper. But we also find another one. This line, the red line is very different with the numerical predictions. This one is the draft, the 9-dimensional draft is 1. That means the bottom of the structure is just located on the internal surface. But here we can find it has a very different trend. Also, the maximum corresponding the Froude number is similar, but the trend is very different. So actually, I don't know how to explain how to play it. So I just come back to check the record of the wave elevations. So these two pictures is from the first picture is yes, this one is a 9-dimensional draft is 0.7. is black cross one. Yes, and this one is is corresponding to this one, and the velocity is 0.12 meters per second, maybe at here. So now we can see the Pinker-Klein elevations. For this one, the wave elevation just touch the bottom of the structure, and we can see some turbulence at here. And this one, because the draft is very deep, from here we can see the very strong turbulence, and we also find that there are some other. It looks like be another another source, and make a series of internal wave at here. It's different with this kind of situations. So maybe it's a strong nonlinear effect or the strong turbulent effect. Due to the difference with the two situations. So maybe I just guess maybe it's this is the reason. Okay, now because we had recorded the Pinker-Klein elevation, so here we should show some pictures. This one is the non-dimensional draft is only 0.5, so it's a shallow draft. From this, we can see clearly with the increasing of the towing speed, the elevation is where the wave elevation is larger and larger, and the wavelength is also longer. Of course, this is not the wave weak. It's just the initial generations under the structure. It's not the weak wave. And we also see that another is with the increasing of the towing speed, we can find the wave crest is apart from the structure, is farther away from the structures. Okay, now let's see another one. That the dimensional draft is 0.73 is deeper than that one. Here we can see the wave elevation like this, because the bottom of the structure is very close to the internal surface. So the wave elevation will be touched to the bottom of the structure. The wave elevation looks like where the wave crest looks like wider and flat. So it's really maybe nonlinear situations. And then with the towing speed, with the increasing of the towing speed, the wave is also larger and is more out from the bottom of the structures. And here it maybe gets the largest situations. Then next, with the increasing of the towing speed, the wave elevation tend to small. Now it's smaller, and then if I think maybe the larger towing speed, and it should be very smaller, very weak, and then the energy will be transferred to the free surface wave, not transferred to the internal waves. Okay. Okay, now I will give some conclusions. I think the most conclusion is the first is the CD will attain the maximum and the corresponding Froude number downshift slightly to the small Froude number and with the increase of draft. And the second is the most important is when CD reach its maximum and when the Froude number is range 0.5 to 0.6. It's much smaller than the critical one, and also smaller than some published results. The next one is for the relative small draft, CD and divided by the square of the non-dimensional draft is depends on Froude number only in the range close to the critical area. and irrespective of the draft. But this conclusion is not suitable for the deep draft case. For this experiment is 1.0 this case. Maybe because of the strong nonlinear and the strong turbulence effect. So the deep draft cases should be pay more attention. Okay, that's my topic. Thank you for your attention. Okay.
I have two questions. Actually, many, but yeah. First of all, I'm just shocked with that Froude number 1/2 instead of 1.
Yeah.
And I understand that Froude equal to 1 is well supported by computations from Fr&gt and from Fr&gt. So this, but the only difference, what I can see, is that the both of them they did computations for non-viscous fluid. And did you try, or do you think about the fully nonlinear Navier-Stokes, fully the nonlinear CFD computations to potentially to extract that 1/2? Was my first question. And second, as I understand, you measured the force only along the channel.
Yes.
It would be great to measure also across the channel and the torque, because I believe that they would be interesting, and there could be another experimental campaign to make your body, that your box, free and tow along the tank, because I believe that vortex shading could be important at certain speed, and also that it's called galloping or something, which is typical for boxes. Yeah, so then it could move in very interesting way, rotating and smashing right or left side of your tank. So it could be very interesting. And actually, it's what's happening in reality. I mean, because there are no carriage which to your iceberg. It's just some ropes. Right. So, okay.
Any comments?
Yes. The second question. I just measure the drag force along the tank only one direction. This is the drag resistance. I didn't measure the others directions force, and actually because this is moving along the towing tank, so the force across the tank it should be 0, but the moment, the pitch moment should be high, but I didn't measure it. Yes. And first question is, you mean that the others results, the Froude number is near to 1, and my experiment test is 0.5 to 0.6. Yes, I think is as the first day, Gou gave the results compared with the linear results and nonlinear results, and the nonlinear results, the corresponding for number is downshift to the small Froude number. So maybe is, but his results is just focus on the slender body. So this nonlinear and the linear comparisons maybe is one reason. So my experiment results, it can be seen the strong nonlinears. And another one is the form geometry is different. Maybe have some different turbulence flow and something else. The potential theory couldn't consider it. Yes.
I do want to have a comment here. So maybe you can take back to the slide with a comparison. Actually,
This one.
Yes. So this is shocking news, Shasa. You're right, and it should be published highly visualized. So okay, so this is the experiment. This is the theory. So that's the ship And I showed even higher, I showed a peak here in my presentation at 0.65. I cannot compute the peak, but it's between 0.6 and 0.7 in my presentation. So everything breaks down because you have breaking. So so when you do this, so why do you divide by b squared? This ratio. That's because the dominant effect goes with the draft, and the normal, or giving the force, goes with the draft, so is b squared. So therefore you have a collapse of the data here. So nothing happens at 1. The message is nothing happens at 1. Nothing happens here at 1, except when you are breaking. So you have the same. So it's a wonderful experimental confirmation of what we see in the theory. But the theory, of course, breaks down when you get the turbulence. This is a very dramatic, this is the worst case. You take the 2D, basically, you have a very narrow tank.
Yeah.
So you have like the worst case you can have. And then you hit the turbulence, but you have here at 1.
Yeah.
So Professor Milo is sitting here, and you have the peak here. So you have kind of the mild excitation. So if you continued with that, I did that, so you could go up here. So then, of course, so here this ratio it's far from the picnic line is 0.25. So it's kind of to go up. So then the peak is at 0.8. So you have a more dramatic draft. The peak is at 0.775. So then you take 0.8. You can still do the computation. You did so I had a big debate with the referee, of course. He didn't believe. So then, so the peak here goes up. So the peak goes like this. And that is the message of Dr. Gou. The peak goes like this. And you see here, you have the small, it peaks here, drops out. Peaks here, it drops out. And you can go down actually to 0.5. You have the peak at 0.5. And then you get the breaking. She's able to put a lot of energy into the waves, and the peak goes up to the low numbers. So suddenly it breaks down, and you have gone through when it breaks down. So it's a very interesting result. Very, very interesting result. Something we cannot compute. Did you get my point, Sarson? See, it's shocking news.
Anyhow, just to make this point clear, if we do linearize theory, and we ignore any viscous effect, we ignore bilge, keel vortices, and shear when the keel is very, very close to the interface, linearized theory, the peak is at Froude number 1.
Yes.
For sure. Okay.
A little bit below.
A little bit below because of viscosity. You can in fact
No,
correct
not
it.
viscosity.
No.
No.
Joe. You can. I mean, it's below, but if you include the peak is infinity in linearized theory. But if you include the viscous effect, you can show that the peak is downshifted, but still it's very, very close to 1.
Yes.
However, if you include probably braking.
Yes.
Wave breaking, and if you include the fact that the bottom of the ship is flat, in fact there is a very, very large shear, and vorticity is generated.
Yeah.
It's a very, very strong effect, which can overcome, the linearized potential flow theory which we are using. So these are really different approaches. Anyhow, I don't know what is the effect of blockage effect in your towing tank. I mean, what was the effect of the width of the channel?
Yes, it should be the effect of the width of channel is not. It shouldn't be equal to the open sea situations. But I'm not sure how the effect about the tank walls on the results. Yes.
But if you really take, I mean, we took spheroid because we use slender body theory. I mean, this is really line
Yes.
distribution of doublet
Yes.
that they do not interact with the interface. The
Yes.
interface is not really doing any overtopping.
Yes.
And the maximum dead water, I mean, phenomena according to Ekman and Nansen is at Froude number minus epsilon. 1 plus minus epsilon.
Yeah.
Linearized theory.
Just make a comment. There are theoretical results for this problem in the weakly non-linear limit, so-called transcritical flow, and they show that the maximum drag occurs at a deviation from the Froude number, less than the Froude number, which increases as n. In the weakly non-linear limit, it's of order m to the power 7 over 6. So in fact, these are the results you'd expect. You'd expect that the maximum drag would skew, and you'd expect as you increase the fractional blockage by the object, you'd expect it to move downwards with Froude number further away from Froude number 1. And the maximum occurs at less than Froude number 1. So, and you get a graph of this shape. In fact, if you do the numerics for the weakly nonlinear transcritical case, not the fully nonlinear case, you'll get graphs like that, but you can then collapse them onto a single graph with a different scaling. And it'd be very interesting to try that scaling on words, on fully nonlinear words.
Yeah. This shocking results. They are, I believe, it's related to the idea of the critical speed. Right? So it looks like the critical speed in that experiment is below the theoretical.
Yes.
But then it's getting even more related to the topic of this workshop, because we are talking about the critical speed of the load moving on ice, and actually it could be different from what we calculate in our model, by our model.
Yes.
And actually, I just asked Natalia, she confirmed that the critical speed measured in that experiment in Birbijan,
Yeah.
just north of Harvey, but
Yes.
not much north of Dalian. So it's different from the calculated theoretically.
Yeah.
The difference, she explained, not very big, and there could be some problems with measurements. But it's still there. So, and we need to know what that. And in your case, it's indeed shocking. It's almost twice the speed is below. Would be great to get explanation.
Okay, thank you for the comments.
Any other comments or let's thank Ying Gou again.
Okay.